Alrighty, so we're going to be starting on a little bit of a different topic with polynomials. You can see in our I can statement we're going to be doing naming and determining the end behavior of a polynomial. So let's get started. Polynomials have two names. It's got its first and its last name. First off is the degree of the polynomial. And the way we find this is just by looking at the exponent. So this would be a fifth degree polynomial. And this one would be a second degree polynomial. And a fourth degree. Anybody have a guess for this last one?
Yeah.
One. It is a first degree polynomial. Yep. So, what happens if there is a more than one degree? Well, more than one term. We always go with the biggest degree. So that would make this a third degree polynomial. It does not matter the order. We always look for the largest term, or the largest exponent. So this would be a ninth degree. A fifth degree. And a guess for the last one? 10th degree. Exactly. So next up, we have the last name, which is going to be the number of terms in our polynomial. A term is any of these individual sections. So if we had let's just do something easy, x squared plus x plus 1. Each individual section is a term. So what is a term? It is we're going to call it a piece of a polynomial. And this is how we name them. If we have one term, it is called a monomial. You'll know, if you know language, mono means one. Two terms, bi, like a bicycle, means two. Trinomial, tricycle, means three. And anything with four or more terms, we call it just a polynomial. We don't need to make one for every single term. So for these next, we're going to circle the last name. Anybody want to just throw out a guess for the first one? It is a binomial, yep. This next one, only one term. Anybody else? Yep. Monomial. And for three terms? Perfect. It's a trinomial. And as we said before, anything with four or more terms is a polynomial. So next up, we're just going to have a little bit of work together, just to put both together, or put both things together. So anybody have a guess for this first one, 7x squared? Second degree monomial is correct, absolutely. Anybody else want to take a guess for this next one, negative 7x cubed plus 9x squared? Third degree. Binomial, perfect. And our last one, remember, we're looking for the largest degree. It does not have to be in order. Fourth degree. And what's the last name? Polynomial, perfect. So we're not going to do this for all of them, but we're going to do it for some of them. So for this first one, I'll just go through these. Our first one is going to be a first degree, and it is a monomial. I'm just going to write the prefix just to save some time. Our next one is a second degree trinomial. Then we have a fourth degree trinomial. A first degree binomial. I'm actually just going to go through all these because it won't take too long. Binomial, I'm just going to write it all out. Fourth degree trinomial. So this is how you brought up with the 0th degree. We do have the option of a 0th degree. If there is no x, it is a 0th degree monomial. And we have another first degree monomial, a third degree binomial, and a second degree binomial. Give you a second to write all that down before we move on. Alrighty. So next we're going to talk about writing in standard form, which is how you'd want to see it, but we're not always going to see it. So we want to put the highest exponent first and write it in descending exponent order. A variable with no exponent has an exponent of 1, and a constant term has a number with no letter always goes last, which is just an exponent to the 0. So when just a little practice for writing in standard form, we always start with our largest exponent, so we'd have 10x cubed. Then we work our way down. We would have, so 9x squared. And our last term, minus 3. And for more practice, what is the name of this polynomial? Third degree trinomial. Perfect. So, anybody want to take a crack at the standard form for negative 10 plus 6x? 6x minus 10. And that is a first degree binomial. So we're going to just do this next one. Luckily, our largest term is already first, so we have minus 4x cubed. We have then minus 9x squared and plus 1, which is a third degree trinomial. I'm going to assume this is a typo again, and that is supposed to be 5v cubed plus v, not 5v cubed v. So for standard form, which is already in standard form, 5v cubed plus v is a third degree binomial. And working through the rest of these, we have 8p cubed minus p squared plus 10p is a fourth degree trinomial. And last but not least, 6x cubed plus 10x squared plus 10x. And that is a third degree trinomial. Why does order help, and why is it important? Order helps you name the leading coefficient. Can I spell coefficient correctly? I don't think so, but close enough. And the leading coefficient. Is one of the important indicators of the graph's behavior. So we could do this. It's not that big deal. So what we're going to do is write a polynomial in standard form with a degree of 4 with a negative leading coefficient, which means our first coefficient, with a y-intercept of minus 3. So this could be literally anything. So it says a polynomial, didn't say trinomial, binomial, or anything else. So that means we need to have at least 4 terms. with a degree of 4, so we know that there has to be at least an x4. We need a negative rational leading, so let's just say minus 2 as our leading coefficient. And we need a y-intercept of minus 3, so our last term is going to be minus 3. Because we know when y-intercept means is when x equals 0, so when x equals 0, all of our other terms go to 0 except for our last term, because there's no x there. And we need 2 more terms, so let's just say x squared plus x. It does not matter what those coefficients are, you can put whatever you want there. Moving on. What is the end behavior of a function? It is what's happening at the end. A little intuitive. Or should be pretty intuitive. So what's happening at the ends, or at the very far ends of the equation, what is it doing? So if we say, I'm going to just write a simple parabola. It doesn't have to be a simple parabola, it could be anything. It could look like this. We could have literally any type of shape. It does not matter. But we're going to just do a simple parabola just to make it easy, keep it simple. So what we're looking at is, give me a different end. So we're looking at the ends. I'm going to use a different number. What are the ends doing? Or where are they pointing? Where are they going? So how we would write this is the limit as x goes to, I'm going to write the negative one, so negative infinity of f of x. So f of x is just our function, and that equals. So if we look as x gets really small for a parabola, we know it is going to infinity, or as it gets really far to the left, it is still going up, it's still increasing. And like we said, for reading location, for this same problem, we'll have limit of x as x gets really far to the right, the function is heading towards positive infinity. So what it's saying is, as x increases, f of x is increasing. And we're only focusing towards the ends of the graph. So if we did have something that looked like this, this would still be the limit of x approaches infinity is infinity, and the limit of x approaches negative infinity is infinity. We're not worried about this middle bit, we're just worrying about what the ends are doing. So, to do this, so as x gets really big, the function also gets really big. So we'll have a positive error that way. As x gets really small, f of x is also getting, well, not also, is getting really big. So it's similar to our parabola, except this middle bit can be whatever you want. Because we're not looking at it, all we're asking for is looking for the end term, or the end behavior. So we don't know what the actual function is, we just know that at the very end, this is what the function is doing. So as the limit of f of x gets really big, as x approaches infinity, or x gets really big, the function approaches negative infinity. So we have a downwards arrow. And as x gets really small, we have the function gets really big. So as we said before, it can literally be whatever you want in between. This is where it gets a little weird. So as f of x gets really big, we're going to draw a thing. So this is going to be at 2. Might have been a poor choice of colors, but so what's saying is, as x gets really big, it gets really close to 2. It does not necessarily get to 2, it could get to 2, but it gets really close, or it approaches the value 2. As x gets really small, x grows indefinitely, or the function gets really big. So literally anything in between here But as long as you have the arrow of it pointing towards and getting really, really close to 2, we're good. Keep the color because I made the decision. So, as x gets really, really big, the function gets really, really big. As the function gets really, really small, the function approaches -3. So we need to mark out where -3 is. And we'll draw an arrow that gets really, really, really close to it. And similar to before, this function can do whatever you want anywhere else, as long as it's still a function. Alrighty. So using that, we're going to write in limit form, we're going to write the end behavior. So we're going to we can always start off by writing the limit as x approaches infinity and the limit as x approaches -infinity of f of x equals of f of x. And I do want you guys to write this whole thing out, the limit of x approaches infinity f of x, because it will help you, and you'll just have to write it and you'll have to know it. So anybody want to shoot a guess for when x gets really, really big, meaning when x is really, really to the right of what value is it approaching? So that's right here. -1, exactly. So it's saying as x gets really, really big, or the equation gets really far to the right, x is going to get closer and closer, or the function is going to get closer and closer to -1. And similarly for when x gets really, really small, it also approaches -1. So as we did before, did not mean to open that. So we always want to write out our limit form. Anybody want to take a guess for the positive limit, or the when x gets really, really big? For b. Infinity. And for the negative limit, when -infinity. So I'm going to write these out real quick, and then we'll do them together. Infinity limit of x minus infinity of f of x equals of f of x equals limit as x approaches infinity, limit as x approaches -infinity, f of x equals f of x equals. Alrighty, so for C, when x gets really, really big, the function does, or goes towards, anybody? -infinity, correct. And when x gets really, really small, or really far to the left side of the function looks like it's going towards -infinity as well. Last problem. For D, when x gets really, really big, far to the right, where is it heading? Infinity. And when x gets really, really small, or far to the left, the function's heading towards -infinity. So that is it for our polynomials. We have our lesson 3 or the practice, the lesson check 3.2 that is assigned, and that is